In this video, I want to show you some examples of using Stokes' theorem to start to solve line integrals and surface integrals. And just as a reminder here, I printed out Stokes' theorem for you just as a reminder. Okay, so hopefully you've seen this before. You had a little bit of experience with it. Notice that the surface S is an open surface and it is bounded by the curve C. Notice also that the curve C is oriented. So when you take a look at that figure, you'll notice that there's a unit normal vector attached to it. And we say that the surface C the surface S and the curve C are compatible with each other. And what does that mean? That means by the right-hand rule, if you grab the unit normal vector with your right hand, your thumb will point in the direction that N points, and your fingers will curl in the positive direction of the bounding curve C. Okay, so that's Stokes' theorem. On a practical matter, gang, Stokes' theorem tells us that under the right conditions, you can replace one integral with another. It may very well be that trying to solve a line integral like this, it may be easier to solve a surface integral and vice versa. Maybe we'll see that in some of the examples. Maybe you'll see that. Also, as a reminder, if you notice, the right-hand side is a flux integral, right? That's a surface integral of a vector field. The curl of a vector field F is another vector field. Okay, so my assumption to keep the video a little bit shorter is that you've got some experience solving surface integrals because they could be a little lengthy and a little tedious, okay? And so hopefully you've got some experience with that so we can keep the video a little bit shorter. Also, it's worth mentioning again, excuse me, that in Stokes' theorem, the surface integral can be evaluated using any surface having the curve C as its boundary, right? As long as the surface is oriented properly with the unit normal vector. So it may be to your advantage to replace one surface with an easier surface, okay? And again, maybe we'll see that by way of the examples. All right, so again, some assumptions. You've got some experience with parametric surfaces, and you have experiences solving surface integrals of vector fields. That'll make this presentation go a little bit easier, I think. All right, with that, here's our first example. Verify Stokes' theorem for the vector field given, and the surface is the upper half of the sphere centered at the origin of radius 2 and bounded by the curve C, which is the circle x squared plus y squared equals 4 in the xy plane. Assume C has a counterclockwise orientation and S has a consistent orientation. I made a little note to myself here, everybody. When we say verify Stokes' theorem, what that means is they want us to evaluate both sides and show that both sides are equivalent. Okay. All right. So just a quick visual of what's going on here. All right, so we have our upper half of the sphere, and it's bounded by the curve C, which is this circle in the xy plane, radius 2. Okay. A unit normal vector to the surface would look like this. Okay. All right, let's calculate the line integral first. All right. Now, for that, I'm going to need the parametric representations of the curve. So I'm going to write for C, let's let R of t be 2 cosine t, 2 sine t, and 0, because it's an xy plane. Of course, the 0 coordinate would be 0. And this will be good for 0 to 2 pi. Okay, notice with my choice for the cosine and the sine for x and y respectively, that's going to give me a counterclockwise rotation of the curve C, which will be compatible with the unit normal vector n. Okay. So our integral then will be replaced with this one. And now we have to put the vector f in its parametric form. Now here's f right here. Okay, switch out the letter x for 2 cosine t. Watch that minus sign now. There's a minus right there. Okay, switch out the third component for y, which is 2 sine t. Of course, we'll dot that with dr. Well, here's r right here. All right, and then we dot our vectors together. Looks like, as a reminder, we multiply corresponding components and add them together. We're going to get 0 times negative 2 sine, that's 0. Negative 2 cosine times 2 cosine is minus 4 cosine squared t. And then 2 sine times 0 is 0. Okay. Now we're going to need the half angle identity because that's an even power of the cosine. Okay. Notice, everybody, that for these two values for my limit, 0 and 2 pi, that sine function right there is going to go to 0. So this second term here doesn't actually make a contribution to the overall value. Also, okay, so that's out. Okay. And then that just leaves me with the variable t, in which case the 0 is not going to make a contribution either. So the final result is going to be negative 4 pi. Okay. All right, now let's evaluate the surface integral. Okay. Now, what I'm going to do for this is, because I can use any surface that's compatible with the curve C in the unit normal, gang, I'm going to actually replace that surface right there with an easier one. So here's my bounding curve C. Okay? And the surface I'm going to replace the upper sphere with is going to be this one. It's going to be the xy plane z equals 0 bounded by that curve C. Okay, see how I did that? Okay, and then the unit normal vector that I'll use for this, for my n, I'm going to use k. And notice that that vector is compatible with the surface and the curve. Okay, but more to the point, can you see how I replaced the upper hemisphere, if you will, that surface, with an easier one? I've replaced it with the xy plane z equals 0 bounded by the same curve, the same circle, x squared plus y squared equals 4. Yeah. Okay. All right. Now, I'm going to leave it to you to verify that the curl of the vector field F is equal to this. Okay, you verify that. And then when I take that vector field and I dot it with my unit normal vector, and remember, I'm using the unit vector k now. I'm going to get -1, which is a constant. So I'm going to stop right there and go right to my surface integral. Okay? Because I know that this integral, when I move the -1 through, the surface integral left is going to represent the area of the surface itself. And what's the area of the surface I'm using? It's that shaded region right there. That circular region right there is my capital S. Circle of radius 2, so pi r squared, to get negative 4 pi, which is what we got with the line integral as well. Okay. All right, let's see. Let's see what we have for our next example. Okay. Use Stoke's theorem to evaluate the line integral for the given vector field, and the surface is the plane z equals 1, bounded by the curve C, which is the ellipse, x squared plus 1/4 y squared equals 1. And again, assume C has a counterclockwise orientation. All right, let's see. All right, so the surface is the plane z equals 1, but it's bounded by the ellipse x squared plus 1/4 y squared equals 1. All right, so that would look like something like this. Okay, and the surface, the plane z equals 1, that's bounded by that ellipse, is right here. All right, so I think once again, I'm going to use for my unit normal vector, I'm going to take n to equal the vector k. Okay, so it's easy to find a unit normal vector for this one, just like it was the previous one. Okay. All right, now, the curl of the vector field, again, I'm going to leave it to you to verify, is this. My unit normal vector, we're going to take to equal k. Okay. And then when I take the curl of the vector field and dot it with n, well, see, we multiply the corresponding components, add together. The only thing that's going to survive is the z minus 1. Okay. And we'll make a note. We'll say also, the differential element of surface area, ds, is equal to the magnitude of n times dA. And we can use our normal vector for that as well. And at the magnitude of that's just 1. So our surface integral then is going to look like this. Okay. Now, notice that on the surface, I'm going to make a note here. So when you go back and look at this later, you know we were thinking. I'm going to make a note to myself here. On our surface, z equals 1, the integrand, which is right there, well, that's equal to 0. And so therefore, since the integrand is 0, the integral is 0 itself. Okay, so we didn't actually have to integrate anything at all for this one, which is kind of nice. Okay. We always say, right? What's the best integral? Right, the one you don't have to integrate. Very good. Okay. All right, here's our next example. Okay. Use Stoke's theorem to evaluate the line integral for the given vector field. This time the surface is the plane, 2x plus 2y plus z equals 6 in the first octant, whose boundary is the curve C. And assume that C has a counterclockwise orientation. Okay, so just get a handle on what we're looking at here. So our surface is the plane, 2x plus 2y plus z equals 6 in the first octant. So we'll use the intercepts to graph it, okay? So let's see, when y and z are 0, 2x equals 6, so x will equal 3. And y will equal 3. Z will equal 6. Okay. Our unit normal vector n would look like that. And so that the surface and the boundary are compatible with the vector, the bounding curve would look like this. Now think about this, right? If the problem said just evaluate the line integral over the boundary, you would have to evaluate the line integral over 3 different curves. Why? Because the curve is made up of 3 different pieces. So you would have to evaluate 3 different line integrals. What the problem is saying is rather than evaluate 3 different line integrals, why don't you just evaluate the surface integral in Stoke's theorem? That way you're just doing one. And it may even be easier in that regard and less time consuming to be sure. Or at least that's the hope. Okay. All right, so let's see. So our vector field is right here. Verify that the curl of that vector field is equal to this. Okay. Now my surface here, I'm going to need a normal vector to this, right? I'm going to need a normal vector. So let me go over here and do a little bit of work. I know that my plane is 2x plus 2y plus z equals 6. Well, everybody notice, my equation can be written like this. G of x, y, and c equals a constant. That's the form of a level surface. And our experiences tell us that gradient vectors are orthogonal to level surfaces. So maybe what we can do here is to find this unit normal vector orthogonal to our surface here, we'll use the equation of the surface itself and calculate the gradient vector. All right, let's see. All right, so the gradient vector is going to be what? 2, 2, and 1. The magnitude of it is, let's see, 2, right? Square the components, add them up, take the principal square root. Okay, so our unit normal vector n it will be this. Also, the differential element of surface area, ds, is equal to the magnitude of n, dA, which we just found right here. All right. Now, when we put all that together, our surface integral, the right-hand side of Stoke's theorem, okay, we need to dot those 2 vectors together, right? So here's my curl vector. Here's my unit normal vector right here. When I dot those 2 things together, we're going to wind up with okay, and then we multiply by the differential element of surface area. Okay. Now, of course, I can cancel those 3's. Now it comes down to the region R, which is the shadow of that surface in the XY plane. Again, that's going to be this triangular region right here. Okay. All right, so let's see. Simplify that expression. And then set up a double integral for the region R. if we integrate with respect to y first and then x. Should get this. Okay, right? Because our region R in the xy plane is right here. And it's bounded by x plus y is equal to 3. Okay. Now, straightforward calculation for this double integral, again, I'll leave it to you for the details, should get -9. Okay. All right. And so this, I like this example because it shows us that if we were to evaluate the line integral just by itself, we would have to find 3 different parameterizations because there's 3 different curves that make up C. We'd have to evaluate the line integral 3 times. A little easier, I think, to do it this way. Okay. All right. Our next example. Use Stokes' theorem to evaluate the line integral for the given vector field to determine the value of the surface integral, okay, where the curve C is a tilted circle given by the following vector valued function. Okay, assume n points in an upward direction. I actually graphed this one earlier. Here's what that tilted circle, everybody, is going to look like. It's going to be centered at the origin. It's going to look something like this. Okay. And if you plot a few points for it, what you'll find is that the orientation of that curve will look like this. Now, the surface that it encloses is this plane region right here. So our unit normal vector n should look like this. Okay. All right, so my vector field, well, that's right here. My R of t is right here. So my line integral is going to look like, oh, I hope I left myself enough room for this. So 0 to 2 pi, okay? The vector field f, now we have to put it in its parametric form now. Everybody, remember, you got to replace all the x's, the y's, and the z's with their parametric counterparts in the vector value function r. And I did not leave myself enough room. That was poor planning. Sorry, everybody. This is r, so dr is going to be the following. This should be sine. Okay. Multiplying corresponding components and adding them together, right? We're calculating the dot product. You should get the following. Okay. Now, integrating over the one complete cycle or revolution of the unit circle, 0 to 2 pi, what's going to happen is that's going to cause this one to go to 0, which you can verify. So all 4 of those are going to wind up going to 0. What's left is negative 2 sine squared. It's 2 root 3 cosine squared. Now, those are even powers of the sine and the cosine, which means you're going to have to use the half angle identities to go further. Okay. Let's see. All right. And then I'll let you take the integration from there, verify the result. Okay. So definitely getting some good practice with some integrals here. Okay. And so hopefully you have enough there, gang. I know they're a little bit time consuming, and just in the interest of making the video uh, not as long as it has to be, I think we'll stop there. I think 4 examples is pretty good. Maybe we'll make another one later, but hopefully you got a good head start right there for examples of Stokes' theorem.